Thank you very much for the introduction. My name is Dmitry. Today I'll be talking about code competitions. I have a cheesy name for my presentation, how to succeed in code competitions. I will talk about what is a code competition from a Kaggle point of view, what makes it so special, at least to my opinion. I'll summarize some experience of what we had with code competitions and like what worked across several of them, what we believe is important. And in general, I just want to say that I do like, I'm among those people who do like code competitions, mainly because they promote like compact, simple solutions, which are based on some creative ideas. But let me start like with a few words about myself. I live in Austria for more than 6 years now. I joined Kaggle around 7 years ago, as you can see from the profile, but I started doing something there like around 5 years. I did 1-2 competitions. I get a gold medal. I was very happy, and then I didn't have time to continue, so I stopped. I stopped until approximately a year ago, and I got to the competitions Grandmaster this year around September. Currently I have 6 gold medals. I ranked 31st according to this slide, but nowadays it's really difficult to keep your rank up. I think today I'm 34th. In a couple of days I'm gonna be 36, I'm sure. Now let's jump to like my most experience in Kaggle, which was around the past year. Basically, it started a year ago when I teamed up with my colleague Philip. We called ourselves the Zoo, and we had like little to no experience prior to Kaggle. We just decided that it's a very good opportunity to learn and try new things we haven't experienced before. So we jumped into the first competition, which looked interesting to us. It was Quora insincere questions. So it was an NLP. We haven't done anything in that area before. So it was really interesting. We got really successful in that one. So we got really hooked, and the whole year we were Kaggling quite hard. We did a lot of different competitions just because it was for us mostly learning experience. So we did this NLP, then we did Santander with tabular data, Lanel with more kind of a time series signal data. We tried computer vision, Aptos, and fraud competition, which is another tabular. Actually, we did 7 competitions overall. You see 5 gold medals. I haven't added 1 silver medal because it doesn't look as cool as 5 gold medals. And there is a 7th competition which is still being scored, so fingers crossed, we might extend our collection of gold medals. What's important to mention is out of these 7 competitions we took part in, 4 were code competitions, and we're actually kind of focusing on those because we like them more. Now a few words about what is code competition. We had a nice presentation today where we were told about like what is behind code competition, what was the idea to introduce it. But for me as a Kaggler, it has a certain twist, a few certain twists. First of all, what makes it different is that you submit not predictions, but you submit the code of your model. You submit Kaggle notebook, and you might have certain limitation depending on the host. So you might be limited on using no external data or no internet connection, so you cannot install new libraries and stuff. But what makes them really different and really special is the left-hand side part of the slide, runtime limits or resource limits. Then I will be talking mostly about these competitions because I believe they add a little bit of a twist and a little bit of some interesting properties. How do I look at them? I usually look at the runtime we have at hand. It can be from a couple of hours to 9 hours. And within this runtime, we need to fit the model. We need to do all the special steps. But unlike a typical competition where you invest everything you can to make the best out of your model, here you have to do it in an efficient manner because you have limits in your resources, limit in the runtime. So you have to pick only the best ideas, drop whatever either is not working well enough or consuming too much time. So a typical story is you have a starting script, you have a data pre-processing there, you have a baseline model fitting, you have inference, and you have some runtime left, which you can invest to improve your results. And then you start thinking what you can do there. You can grow a model bigger, you can add more features, you can fit the model longer, you can get creative over there. And that's the general perspective of how I look at such competitions. That makes it a little bit special in a way. First of all, due to the limited runtime, like it is no go for like heavy, overcomplicated, over-engineered model. It's just not going to fit. So it promotes lightweight solutions. You can easily test different things. So you have a baseline model, you want to change it a little bit. It's going to cost you pretty much the runtime, which is fixed. So it's, you cannot fit the pipeline for that long because you won't be able to submit it. So all the testing will be fast, and you will end up probably having a very, very well optimized model in the end. Same actually applies to like trying new ideas from scratch. I personally find it mentally very difficult to give up a very complicated model that I have been working for weeks and start it over, compared to a model which runs within a couple of hours. So that actually emphasizes some focus on creative ideas, creative solutions. Another thing is that you have your hardware there, you have the software installed, so it's easy to jump into the competition, and sometimes it has more competitors, more competition going on there. And it's, I believe it's a little bit more fair because all the competitors are a little bit, not fully, but more equal with regards to the hardware they have. Now let's talk about what does it imply towards me as a Kaggler when I approach such a competition. First thing is probably by far the main message, the main tip for Kaggle competitions. Try more, fail fast. This is what actually makes the success. You never know upfront what is the best solution for the task. You never know what's going to work, what's not going to work. So you're going to be trying a lot of things. It can be feature engineering, it can be different data structure, model structure, augmentations, TTA, it can be anything, and sometimes you really have no idea when you start the competition what you're going to end up doing. But you know for sure you will try a lot of things. And with kernels, it is everything is running pretty fast because it's time limited, so you will be trying even more than usual. Let me show you how it looks like on an example. This is a funny looking kind of weird Christmas tree, I guess. This is from one of the latest competitions we took part in. That was a kernel competition. That was actually NFL competition. And as soon as it was a kernel competition, we did almost all our work on Kaggle platform in the notebooks. So the platform was basically tracking our work. And what we did after the competition ended, we just pulled through Kaggle API the notebooks and the connections between them. Because the way we usually work, we take the current best model, we fork it, and we try to improve it. So I was able to plot a graph of all the commits and forks in between them to emphasize how we started with a baseline model on the left-hand side and ended up on the right-hand side with a final model. So basically, the red dots represent the path which actually led to the final model, while green were all the tries of model structures, model parameters, which had no contribution to the final model at all. Of course, they were not useless. We learned something, but you can see that we tried a lot, and most of what we tried actually had no contribution to the final solution we had. Overall, there are 500 commits here on the slide, and this is not counting the commits of the different structures of the model we've tried. So it's quite a lot of work, and quite quite a lot of reward whenever you finally get an improvement. If you think about it, there are like 500 models there, and you need to pick one, the best one. And how would you do that in a reliable manner, given that you try so many different ones? Our strategy is simple. We go crazy on cross-validation. We do it in quite a regular manner, usually, if it works. Sometimes you need to adjust depending on the data, of course. And we do, by default, k-fold cross-validation. This is an example of 5-fold cross-validation. So you split it into training validation, you train on 4-fold, predict the 5th one, then you stack together the validation predictions, and you have a vector of predictions on the whole set. Nothing new here. Usually there's like a random factor involved in the model, especially in neural network. So what we do, we repeat the procedure several times, in this example 4, and average across. That ends up with like 20 runs of the same model over and over again. And usually we're not even happy with that. We repeat it a few times more to check whether CVs of that bag of models is still stable. Why do we do that? Is to trust our CV as much as possible. What can be the rewards? The rewards can be the correlation between cross-validation and leaderboard. So what we look at, we submit something, we know the cross-validation score, we check the leaderboard. And what we want to achieve is if a model improves cross-validation, then it should improve the leaderboard. Otherwise, we're kind of lost and we don't know what exactly we're doing. And in a very perfect case, in a perfect world, it can be even linear. You might think that it's a generated data, but actually it's a data from one of the competitions we participated. I've never seen such a correlation ever before in my life, and probably I doubt I will see ever again. But whenever we saw that, we trusted our approach of modeling and cross-validation very much. I mean, you don't have to do any more leaderboard submits. You kind of have countless submits, because if you know CV, you know almost precisely what would be the leaderboard score. You also trust your model, and it's also going to be easy for you to pick the best one in the end, because, well, it's going to be the best one on CV, and obviously it's going to be the same one would be best on the leaderboard. Another important topic, and probably it's kind of underappreciated, is teaming up. In general, I do encourage everyone to team up, because this is an amazing experience you gain from working with someone else. It also helps you to think about the problem from different angles, and just remember that it doubles the efforts you can spend on a task. And if you're planning to try a lot, that will help a lot. Observing other Kagglers, I would say there are like 3 strategies of how people team up on the leaderboard. The first one I like to call team up with Grandmaster. I see some people who are doing quite well on the leaderboard and getting stuck. They're looking for someone experienced in the area, or any Grandmaster who can team up with them and improve the solution. That works quite successfully often, and you might hope for getting the gold medal in the end if it works out. The second one is merging solutions. So you have your model, you made the best out of it, but you get stuck. So you find another team with a similar score, you merge your efforts. Sometimes you just average your predictions, and you have the improvement. Third one is when you think about your team upfront. Maybe you think about like splitting the tasks among the team, so you get one person who's really good at feature engineering, another one in neural networks, and one more guy who's amazing in stacking. And you can form a team upfront and then invest time in as a team since the very beginning. Or you can have like team work focus, so you have 2-3 really good guys doing being able to do everything, and you just share your ideas and thoughts. For kernel competitions, I would say the third one works the most the best. The second one doesn't work at all, basically, because you cannot like easily merge the solutions. But when you team up, and even if you don't, but especially if you do, you have to keep your code clean. You're going to be running it over and over again, changing the parameters, looking at the same line of code every day, basically. So you don't want to look at some dirty code. And keep in mind that other people in your team will be doing the same thing. So keeping your code clean will save a lot of efforts from your side, a lot of efforts from your teammates' side, and can minimize the risk of your doing something wrong in the end just because you had some code there for a while and you forgot to remove it. Keeping your code clean is not all of it. I believe you also it is also important to optimize your code. I think it's also an area which is a little bit underappreciated in general. And you can start from like the obvious things, like removing redundant things, or like taking a look at what you've done in a dirty manner and just do it in an efficient manner and so on. Maybe parallel execution and so on. Why is it important? Because this is going to increase the amount of main resources you have, the runtime for your kernel run. Let me give you an example of how we did it lately. In a nutshell, that was a competition when we ended up feeding neural networks on CPUs because, well, these were this was a kernel competition CPU only, and we saw neural networks of a particular structure work well. So we were happy with the model we had. We were running it, and the feeding was relatively fine, 31 second per epoch. We're okay with the results. But when we looked at the resource management tool, we saw that CPU is loaded by 233%. That means that out of 4 cores, we have 2 and a little bit more are loaded. So obviously the resources are not efficiently used. So what we did first is like, that was PyTorch, by the way. We just took away the option from PyTorch to multi-thread and just gave a single thread. So first step, we see CPU is close to 100%, so it's working. And interestingly, the runtime increased only a little bit, 39 seconds. Why did we do that? Because at that point, we could have we switched to running 4 of them in parallel. So 4 single-threaded PyTorch neural network feedings running on a Kaggle kernel. That ended up, I believe, because of like specific hardware structure, because I think there's like two physical cores with multi-threading, not 4 physical cores. That led to some increase in the runtime. So we started with 31 seconds and we ended up 65, twice slower. But if you think about it, we're feeding 4 models instead of 1. So we're actually doing the work almost twice faster than we did before. So we cut the runtime of our feeding almost in half. This idea also worked well for cross-validation on GPUs. We did the same trick on GPUs, and there you can go a little bit more crazy, do more than 4 models, 10, maybe 12, depending on the machine you have. And we ended up running our full CV 4 times 5, 20 models within 15 to 20 minutes. So we could have tested like 3 to 4 ideas per hour. Whenever you have like extra time, you think how to invest it, and one of the typical ideas, typical approaches is to blend or to stack models. And this is an example from one of the 5 years ago competition. It was auto classification, one of the good tabular competitions where stacking was really important. So you fit several different models of different structure and so on, and then you think how to combine them, take an average or build another model, layer on layer, and so on and so on. But the question is it really worth it? Should I blend in a kernel competition? My answer is, well, yes, but actually no. I do believe it's a good idea. I do believe it's a powerful one. I tried every time, but so far it has never worked for me in a kernel competition. It was always more worthy to invest in something else, in improving a single model rather than thinking of like stacking a bunch of different ones. For instance, what always works and what is always there is bagging, especially for neural networks. That's also an example on one of the competition data sets. The gray lines are individual runs of 4 neural networks with different random seeds, and we observe the validation loss. So it increases, it converges, but we see it's quite random. Some people try to fix random seeds, some even try to optimize random seeds, but be aware that this random behavior also is translated to leaderboard. So if you fix the seed, you don't know whether it's going to be an optimal seed on leaderboard. One thing which always works is just taking the average of those, as simple as that. It always performs better than the best out of the bag model, and it's way more stable. Here we see that if we would have taken an average at each epoch, it would have been better always, and the final bag is quite significantly better, and it's way more stable. So if you would repeat the same thing over again, you would see that, of course, there's also random effect, but it's not as significant as with individual runs. It is costly because you have to run the full model fitting several times, but it's rewarding. If you don't have the luxury of running the model that many times, there is a nice trick which we learned, which we haven't yet used, but I think we will at some point, called Snapshot ensembling. So you take a single model and you take a snapshot at different epochs and just average those, treating them as a bag. That gives you improvement over the best individual epoch. It makes it a little bit more stable, but not as well performing and not as stable as a bag of several runs. But on the other hand, you pay very little to no price because you don't have to run the same model over and over again. These are I described a couple of tricks of how to improve the runtime and not hurt the model, but win some time to maybe make it more complicated or increase the size of the bag. In the first competition in Quora, we tried even going further and trying to make the model performing a little bit worse, but wins quite a significant amount of runtime. The idea was that we saw that we're able to fit 2-3 neural networks within the time, and it was very unstable. So we were aiming at at least 8 models. And we found a trick of how we can do that by actually hurting individual models, but improving on the bag. The competition itself, in a nutshell, was the following. We had to classify short sentences, and we were given word embeddings up front. And in the end, it was just LSTMs and figuring out the better structure of the neural network. So what we did first, we embedded all the words and we put it into the matrix. What you have to do upfront is specify the maximum length of the sentence, so all the embeddings fit a nice matrix. And you add blank embeddings to the end to fit the maximum length of a sentence. So we see a lot of blank embeddings, which are in the end quite useless for the model, and they're just consuming resources. So if it would have been possible to remove all of them, we would have won quite a lot of time. We used Keras for that one, and quite quickly found out that the common approach is to define the maximum length of a sentence at the batch level rather than on the whole sample. This picture is not extreme as the real data, because in real data there's 1 or 2 sentences which are extremely long and they mess up the whole picture badly. So when you do it on the batch level, you only mess up a couple of batches, so the model runs quite fast. That gave us a lot of boost in speed and the same accuracy of the model. So it was nice, but we wanted to go even further, and we tried two ideas. One was as simple as sorting the sentences by length up front. So the picture would look like this on the left-hand side. So the batches contain only sentences of similar size, so we don't lose too much. We don't introduce too much like blank embeddings in the batches. What was the result of that experiment? The speed was dramatically improved. That was a significant one, but unfortunately the model was quite worse. The explanation is quite simple. We stopped mixing like completely different sentences in one batch, so the model is not converging as well as it could have. But it was a nice experiment. Maybe that will work in some other competition. So we had to switch back to the random order of sentences. But in order to increase the speed, we did the following trick. We believe that like very long sentences are not worthy. So we cut it at like certain quantile, physically dropping some of the data, some of the training data, hurting the model, but not that much, and improving the speed quite a lot. So individual models were worse, but we were able to fit more of them, average more of them, and we ended up improving the overall performance. These were just a couple of tricks, and usually they're very competition specific. The only tip I personally have, which applies for all the competitions, is try to go for the win. If you go by the book, then you will never perform better than most of the people. Try to do something exceptional. Think maybe what would the winner of this competition try to do, and try to do that. There's a good chance that you will fail, but it will be very rewarding if your creative idea will work and you will be at the top of the leaderboard. Thank you very much.